you switch it from someone else? Zobaczymy, jak stanie i sobie dostać. Tak, ładnie powinien wystąpić na całą wygodę.
Tak, mamy to wystarczy. Zapewne na stronie.
Przepraszam, czy ja ten mikrofon mogę wyłączać i włączać, czy lepiej tego nie robić? Czy...
Nie,
Jest teraz wyłączone.
Nie, teraz jest włączony.
Czerwony przytrzymać.
Ale wtedy on coś robi, tutaj pisze, pyta mnie.
Przytrzymać, tak.
A, przytrzymać dłużej. I co, i można to robić, tak? To znaczy...
W zasadzie tak, jeśli rozładuje się baterię w trakcie, to nie mamy tutaj zapasowych, tylko na dyżurce.
Okej, dobra. A do tych pytań mamy tylko jeden mikrofon, nie mamy więcej, żeby tam... Ja.
niestety wiem.
Co, jak go włączę, to... Okej, działa.
Coś tego przybliżenia. Się przesunąć, to jest tak.
Okay, so welcome everybody. So welcome to the second plenary talk today, the second and the last plenary talk today. So Piotr Nowak will talk. So Piotr doesn't need probably more introduction. We saw word about him on Monday. So just to remind you, he's a recipient of the main Banner Prize of the Polish Mathematical Society this year, and this was awarded because in recognition of his work on property T, on Każdan's property T, especially his work on the Każdan property T for group of automorphism of free groups. And his lecture will be exactly about this. Please.
Thank you very much. Everyone hear me?
Yes.
So I'd like to say that it's a great pleasure to be here at this joint meeting and to be visiting the city and this university. I'm really enjoying this conference. So I'd like to talk about property T for automorphism groups of free groups. So here is a rough outline. So I'll start with some definitions and explanation why property T is important, then discuss some examples, and then move on to the main result that I want to present. Okay, so let's start with the definition. So property T is considered a rigidity property for groups. So what are the objects of interest here? Usually we will be looking at a locally compact group. So here are some examples. So compact groups, finite groups, Lie groups in particular, SLNR, SLNC, SLNZ. So these are groups of n by n matrices with coefficients in the appropriate coefficient ring, and these are groups of n by n matrices with determinant 1. Discrete finitely generated groups, which can be given by a presentation like here with S1 through Sn being generators and R1, R2, and so on being the relations. So here's a presentation for Z squared, the free abelian group on 2 generators, and here's the free group, which just consists of, so here we have 2 generators which commute, and the free group on n generators is given by n generators, and there are no relations between them. Right, and then also of interest are lattices and Lie groups. So these are certain discrete subgroups in Lie groups. So for instance, SLNZ. So these are n by n integer valued, n by n matrices with integer coefficients and determinant 1. Okay, so these are the main objects. So what is property T? So property T has a lot of different characterizations. And the simplest one of them is the one written here. So this is not the original one, but this is the easiest one to formulate and the easiest one perhaps to understand. So the locally compact group has property T if whenever you take a continuous action of G by affine isometries on a Hilbert space by this group, there is a global fixed point. Okay, so this is a very strong property. So this should be visible right away, because in principle, well, for any group you should have a lot of actions by affine isometries on a Hilbert space. This shouldn't be a very restrictive condition. However, in some sense, this definition tells you that all of these, whenever you have a property T group, all of these actions are in some sense trivial. Okay, so as I said, this is not the original definition. However, it's very useful. So we can right away see that that compact groups, or I'll be more interested in discrete groups, so finite groups in particular, have property Ty, because if you look at a compact group which has such a continuous action by affine isometries on a Hilbert space, you can average over the group, right? So if it's easy if you have a finite group. If you have a compact group, you can use the probability, the Haar measure, which is a probability measure, an invariant probability measure. Okay. However, it's easy to see that many groups do not have this property. Okay, so I can take Z acting on the Hilbert space given by the real line, and it acts just by translation. All right. So then I don't have any fixed points. Okay, so it's clear that this group does not have property T, and this generalizes to all finitely generated abelian groups, because up to torsion they are just copies of sums of copies of Z. Okay, and another example is the free group. So this is the group generated by n letters with no relations, and you can act on it with an infinite dimensional Hilbert space in such a way that whenever you take a word and extend it by a new by the next letter, then this acts in a new direction, in a new orthogonal direction. Okay, so this is a very vague description, but it's possible to write this action fairly easily. And because of the infinite dimensionality of the Hilbert space, this actually works. Okay. So property T was introduced by Kashgan in a very short but very influential paper in 1967. And he used a different definition. So he was interested So the definition that he used was coming from representation theory, and it can be formulated in the following way. So you can look at the so-called unitary dual of a group. So that's the space of equivalence classes of irreducible unitary representations. And there's a certain topology that you can put on this space. It's called the Feld topology. And the definition that he was using is that G has property T if the trivial representation is an isolated point in this unitary dual with the Feld topology. Okay, also in that paper, he showed that there are infinite groups with property T. Okay, so he showed that SL and R and lattices such as SL and Z have property T. So this is to date the most classic example of a group of property T, of a group with property T. Okay, so why would you care about this property? Okay, so it's a strong property that kind of follows from the definition. But why would you actually care about it? So I'll mention two applications which are quite useful. The first one is expanders. Okay, so expanders are certain families of infinite families of finite graphs. So let's start with a finite graph. It consists of vertices and edges. And for every set, whenever I choose a subset of the vertices, I can define its edge boundary. Okay, so this is a notion that's somehow transplanting definitions from Riemannian geometry to graphs. So the edge boundary of a set of vertices inside my graph is the set of those edges such that of those edges which have only one vertex in A, so those which connect A to the complement of A. Okay, so if I choose this set, then this will be my edge boundary. Okay. Okay, and I can also define the Cheeger constant. So the Cheeger constant looks at the minimum over all sets in subsets of the vertices of this quotient, where you in the numerator you look at the cardinality of the boundary versus the cardinality of the set itself. Okay, so if this constant is large, this means that you have that every set has a large boundary. This is what it is, right? And in general, this constant measure the connectivity of the graph, in the sense that, well, if every set in your graph has a large boundary, that means there's a lot of edges connecting it to the complement. So it's, for instance, hard to separate the graph into two different pieces by just taking out edges, right? So you have to take a lot of edges out for the graph to split into two parts. Okay, so whenever you have a finite graph, this constant is, of course, positive. However, when you consider expanders, what you are interested in is having an infinite family of finite graphs, and then looking at how this constant behaves for this family. Okay, so in general, you would like to have families of graphs with this Cheeger constant being bounded uniformly away from zero. Okay, so one example where something like this can happen are complete graphs on vertices. You can see that there is a lot of connections between the vertices. The problem is that the degree grows, right? And it grows quite fast. So what we would really like to have when we talk about expanders are families, infinite families of finite graphs, where you have this Cheeger constant bounded away from zero uniformly, but the degree is constant. Is uniformly bounded away from above. Okay, so that would mean that we have large sets with that every set has a large boundary, but also in general we don't have that many edges in our graphs, right? So the graphs that we get are at the same time sparse and well connected. Okay, Okay? So this is, when you think about it, this is actually quite a bit counterintuitive. So here's a formal definition. So a family of expanders is a family of finite graphs such that these Cheeger constants are uniformly bounded away from zero, degrees are uniformly bounded from above, and of course the graphs are getting larger and larger, because that's, otherwise we would, this wouldn't be interesting. Right, so these expanders are very useful. So first of all, the obvious application is that you can use them to construct robust networks, right? So if you use such a graph to construct some kind of a computer network or I don't know, well, some kind of a network. If this graph that you get is an expander, that means if you cut some of the connections, the network will still will not fail, right? So this is important in many contexts. So this is one obvious application. However, there are some other applications in computer science. So these graphs are used for constructing various algorithms. So here's an example, a particular example. So expanders were used to construct the so-called optimal streaming algorithms. So what is a streaming algorithm? This is a screenshot from what is now called X and used to be called Twitter. And on Twitter, what you have on the side here is a list of trends, right? So what this list tells you is it tells you at the moment what are the most popular phrases that are appearing in the messages that are being posted, right? And so you need an algorithm for that. And this is exactly what streaming algorithms do. They create they can sort through data and pick out such phrases. So this is not an easy task to do because this algorithm acts as sort of a gate, and the data passes through just once. Okay, you have millions of or hundreds of thousands of messages being posted every second on this website. So the algorithm sees each message only once, and based on this information, it has to sort out the important ones. Okay, and it has to do it quickly, right? So some of the such algorithms exist, and the optimal ones that were constructed were actually constructed using expanders. So here's an article, if you would like to read about this. Here's an article from Quanta that describes this construction and how it works. Okay, all right. So that's one application. Now, in general, expanders are difficult to construct. Okay, so the definition, I think they were defined in the 50s, and then there was a probabilistic proof that they exist, but there was always a question of how to actually construct them. And the first construction of explicit example was due to Margulis. So he did this in 1977, and he realized that once you have a group with property T, you can use this to construct expanders. Okay, so he proved the following theorem, which is actually not difficult to prove. The main input here is that what he was able to see is that that you have these two properties from seemingly two different areas, and he was able to connect them. Okay, so he showed that if you start with a finitely generated group which has property T, and it is residually finite, which means that there exists a sequence of finite index normal subgroups, which are getting less and less dense in your group, so their intersection is trivial, then the sequence of Cayley graphs of the finite quotients of G by these subgroups is a sequence of expanders. Okay, so here's an example. So he used Kazhdan's proof of property T for SL3. If you take the KD graphs of SL3 Z mod P to the power IZ, then this is then these are expanders because SL3Z has property T. Okay. All right. So there's another area in which expanders are useful, and expanders and property T, and this is index theory. So the Atiyah-Singer index theorem is often mentioned to be one of the most important theorems of the 20th century, and it's a statement about the index of elliptic operators in compact manifolds. Okay, so the Fredholm index of an operator on a Hilbert space, it's the difference between the dimension of the kernel of T and the dimension of the co-kernel of T. So an operator's Fredholm is if this index is finite, which means up to some bounded piece, it is invertible. Okay, and the Atiyah-Singer index theorem, this is the theorem that Atiyah got the Fields Medal for, and Atiyah and Singer both got the Abel Prize for. They showed that if D is an elliptic operator on a compact manifold, then the index of this operator, understood in this analytic way, can be actually expressed in terms of topological data. Okay, so these are some cohomology classes evaluated on the fundamental class of the manifolds. Okay, so this was a huge theorem that gave a bridge between topology and analysis. So it can be so the proof goes via K theory. So you start with an elliptic operator, you have this analytical index, but you can also, using the symbol of the operator, you can construct the K3 class, and then you can construct a map, which is this topological index, and they show that these two are the same. Now, there is a generalization, or conjecture generalization of the Atiyah-Singer index theorem, which is the Baum-Cohen conjecture. So this is a conjecture which was defined originally by Baum and Cohen in the 70s, and then turned into this form by Baum, Cohen, and Hickson. And it's a conjecture about a certain homomorphism in KK theory. So there's the index map, the so-called assembly map, that goes from I'll just say the words, but it's these objects are actually require quite a lot of work to define. So this is the representable equivariant KK theory of the classifying space for proper actions of the group with coefficients in a C-star algebra A, and this maps goes into the K theory of the reduced cross product of A by the action of G. And so the conjecture says that this map is an isomorphism for both of the indices. But the general idea is the same as the Atiyah-Singer index theorem. So, the idea is that on the left-hand side, the K homology classes are some kind of generalized homotopy classes of some generalized elliptic operators associated to a group. And on the right-hand side, you have K theory classes which play a role of the generalized Fredholm indices. So in the previous slide, the index in the Atiyah-Singer index theorem took values in Z in the integers, and that Z is the K theory group of a point. Okay, so that's how. Yeah. So this is essentially the same idea, but just generalized heavily. Okay. So this conjecture is quite well, quite influential. So it has a lot of applications, implications in topology of manifolds, and it allows also to, in certain cases, say something about the K-theory of the C-star algebra on the right-hand side. And it's been proven for many groups. So here are some classes of groups for which this conjecture was proved. So abelian amenable, free hyperbolic. So this was done by Vincent Lefort, Igor Miniev, and Gouverneau. And for amenable, so which admitted proper affine isometric action on a Hilbert space by Dixon and Kasparov. So this last condition here is a condition that is very much opposite to our definition of property T. So our definition said every proper affine isometric action on a Hilbert space has a fixed point. This condition here says there is an action which doesn't have a fixed point in a very strong way. So the orbits go to infinity. Okay, so one of the big open questions about this conjecture is, does SL3Z satisfy the Baum-Kahn conjecture? And the main obstacle is property T and various strong forms of property T. So why is this the case? So for certain choices of coefficients, there are counterexamples already, and these involve certain groups that contain expanders in their Cayley graphs, so-called Gromov monsters and Osaida monsters constructed by Damian. So these groups give counterexamples to some versions of these conjectures. And property T is in some sense behind these counterexamples because in general, so the heuristic is that proving Baum-Kahn conjecture using the standard method for proving it, the so-called Dirac-Gould-Dirac method, in some sense boils down to showing that once you have two unitary representations of the group, the trivial one and the regular one, that there is a path of representations connecting these two. However, as we said, Kazhdan, the original definition that Kazhdan said, that Kazhdan used was that if G has property T, then the trivial representation should be an isolated point in the unitary group. So in principle, there shouldn't be any path connecting it to other representations, right? So this is the heuristic of why this is important in this context. Okay, there are some other applications of property T, and these involve rigidity statements for group actions and group algebras, so various operator algebras associated to a group. So here's an example of a rigidity theorem for smooth action. This was proved, I think, in 2003 by Fisher and Margulis. It's the so-called local rigidity theorem, and it states that if you have a property T group and it acts smoothly on a smooth manifold, so there are two smooth actions on a smooth manifold by this group, then if they are close on the generators, then they actually have to be conjugate. Okay, so this is a very strong statement, and this kind of rigidity is what you can often squeeze out of property T. Okay, there's also a similarly flavored program for phenomenon algebra started by Sorin Popa, and in that setting, what you do is you take a group and you take a phenomenon algebra associated to the group. That's just a completion of the complex group ring and the weak star topology inside B of H, the algebra of operators on a Hilbert space on L2 of G. And that gives you a phenomenon algebra, and sometimes you have some kind of a group action, and you can ask also for a cross product. And in general, you want to know, does the algebra remember the group, or does the algebra remember the action? So if the algebras are isomorphic, are the groups or the actions are isomorphic? Okay, and in the presence of property T, you can actually prove theorems like this. I mean, so there's a number of results in this direction. They are always quite involved, yeah. Okay. So this is a brief list of why property T is something that people care about. Okay, so why is this something that one might be interested in proving? Okay, so what are examples of groups with property T? So until recently, there have been two main methods of proving that a group has property T. One is relies on algebra or on the algebraic structure of the group and some knowledge of representation theory, and the other one is the so-called geometric or spectral method. So the first one was the one used by Kajdan. So he showed. So here's a reminder of what he showed. So for SLNs, which is really the main case you want to prove, his method was relying on the fact that SLNZ is a lattice inside SLNR. Then you know a little bit of the representation of the behavior of unitary representations for SLNR, but also you have SLNR. This is a matrix group, so it has a lot of structure. Okay, so in particular, if you have SLNR for some large n, there is, for instance, a lot of copies of SL2 sitting inside SLN, right? And so what he did is he was able to show that from the existence of these fixed points for a lot of subgroups, for some very thin subgroups inside SLNR, you can actually get these fixed points for the whole group. Okay, so this relies really heavily on the algebraic structure and on the fact that you have an extremely nice group to work with. Then there is the so-called geometric or spectral method that goes back to the work of Garland in the 70s. It looks at eigenvalues of the Laplacian on the so-called link of a complex. Okay, so in a two-dimensional simplicial complex, the link of a vertex is a graph in which you it's a finite graph. It's given by the vertices are given by the edges that connect to a given vertex, and then you connect them by an edge if they span a simplex, right? A two-dimensional simplex. Okay, so these are finite graphs, right? So for every vertex, I have one of these links, and I can look at the smallest positive eigenvalue of the discrete Laplacian, the graph Laplacian on the link. Okay, so the graph Laplacian, these are finite graphs, so I have L2 on the vertices, and the Laplacian is some finite dimensional operator. An operator on this finite dimensional space. So it's just a matrix, and I can. It's a positive operator, so I can look at the smallest non-zero eigenvalue of the Laplacian. And here's a theorem that emerged in the late 90s. So here's the general formulation is that if G acts properly co-compacting on a contractible two-dimensional simplicial complex, such that every link, the link of every vertex has this lambda 1 strictly greater than 1/2, then the group has property T. Okay, so this was done more or less at the same time by several groups, by Bollman and Jacek Świątkowski, who was sitting over there, Pierre Pansou and Andrzej Żuk, and then also extended later by Demara and Januszkiewicz. And so this is a method of very different nature, right? So because you look at a complex, and you look at the local geometric structure of the complex on which your group acts, right? And then you say, well, if something is happening locally, then I have this global, property that I have for my group. Okay, and the general idea is that this condition lambda 1 strictly greater than 1/2 should be some kind of a positive curvature condition for the orbit of the action on a Hilbert space. So here are some examples to which this applies. So you can take groups acting on certain types of buildings. So buildings are certain very nice simplicial complexes which are built in the here. So here's an example. You have the plane triangulated in this way, but also at every edge you have another simplex sticking out, just like here. And then this new simplex lies in a new plane, which again every edge looks like these guys here. And so it's kind of like two-dimensional branching happening. Okay, so here's a picture of what the link looks like. It's quite complicated, but it turns out that so it looks quite complicated, but it turns out that these eigenvalues of the Laplacian were computed for some other reasons, and they turn out to satisfy the conditions of the theorem, and then this works. So these are the main examples here. Okay, so what I would like to describe now are the examples that we were interested in. So let me define the groups that we will be looking at. So the free group, the Fn will be the free group on n generators. So you just take n letters and no relations, and that's so the group of words on these letters is your group, and you can only cancel a letter with its inverse. Then we look at the automorphism group, so all the bijective homomorphisms from this group to itself. Okay, so that's all Fn. Then there is a specific subgroup inside this group, which is called the group of inner automorphisms, and those are the so-called easy ones. Right? So the ones that are given by conjugation. So I fix an element A, and to an element A inside my group, I can associate an inner automorphism which takes G to the conjugate of G by A. Okay, so those are the trivial automorphisms, the inner ones. And then I can form the outer automorphism group, which is just a quotient, right? So I'm getting rid of all the easy ones. Okay, so the question that I want to address is: do these groups odd Fn or out Fn have property T? Okay, so this was an open question for a while. So the first appearance in print is in Ali Slobodski's book in 1994, but it's been around earlier. Why does this question even make sense, right? Because it's so we know SLNs have property T, but why would you come up with this group when something asks about this particular example? So there's a particular analogy that is that serves as motivation for a lot of results in geometric group theory. Okay, so there are three families of groups which happen to be connected at index 2, so at their start. Okay, and these are the outer automorphism groups of three groups, linear groups, and mapping class groups of surfaces. Okay, so these we know, these are just invertible matrices over Z, and mapping class group. So if you have a surface, the mapping class group is the group of self-homeomorphisms of the group modulo the relation of isotopes. So a homotopy in which every element is a homeomorphism. Okay, so one of the big motivations in geometric group theory is to take statements that we know for linear groups, right? So there's a lot of theorems that we know classically for linear groups, and then try to prove their counterparts either for mapping class groups or for automorphism groups of free groups. Okay, so this is some kind of general theme, and this is precisely what motivates this question. So for automorphism groups of free groups, we will answer this now. I can already say that for mapping class groups, it's still open. Okay, so what do we know about this question? So what was known earlier? So it was known that the answer is negative for n equal to 2 because of the statement from the analogy from the previous slide. So odd f2 surjects obviously by definition onto out f2, and this is equivalent. This is isomorphic to GL2Z. Now, it's easy to see that property T is inherited by quotient. So if odd f2 would have it, then out f2 would have it, and we know that GL2Z does not have property T. Okay, so then for n equal to 2, it's not equal. We don't have property T. And it was also known to be negative for n equal to 3, and this is due to a theorem of McCool, which was proved in a completely different, using a completely different motivation. So for some other reason, he showed that there is a surjection from odd f3 onto Z, and again, if odd f3 would have property T, then Z would have to have it, and we actually already saw on one of the early slides that Z does not have property T. And there was another proof by Grunewald and Lubowski that it surjects virtually onto f2. But for n greater or equal to 4, this was open. So the theorems that I want to present are two theorems. The first one was proved with Marek Kaluba, who was a postdoc at IMPAN, and Taka Ozawa from Kyoto. And the second one, so the first one says that OF5 has property T. And the second one was proved with Marek Kaluba and David Kielak from Oxford. And this does the infinite case, so OFN has property T for n greater or equal than 6. All right. So which method should be used to prove this? Well, it turns out that neither of the previously used methods. And the reason is the following. So OFN has a very complicated algebraic structure. Okay, so it's easy to define. I mean, you can always take a group and take a group of automorphisms of any group, right? The definition is there. But then to actually learn anything about the algebraic structure of this group of automorphism, that's not easy. Okay. So that's the first issue. Then, that's what happens if you would like to try to mimic what Kashdal was doing. And then if you're trying to use this geometric or spectral method, then you also run into problems because in order for that to work, you need some kind of a nice complex with something nice happening locally, where you can control the local geometry, on which this group will act nicely. Okay, and that's also an issue. I mean, we don't have models of this. So it was necessary to use a new method, and this is an approach that combines algebraic positivity in the group ring and semi-definite programming. Okay, so I'll recall here what a group ring is. So a group ring over the reals, you can have other coefficients here, but the group ring over the reals is these are finally supported functions. So G will be discrete. So these are finally supported functions from G to R with convolution as multiplication. Okay, so that's the group ring. And if I choose a finite generating set for G, I'll assume that that my group is finitely generated. then if I choose a finite generating set, I can define an element inside the group ring, which is the so-called group Laplacian. Okay, so this is the element 1 minus the average over the generators of their characteristic functions. Okay, so it's 1 at the identity and minus 1 over the cardinality of S on the generators. It's a very simple element inside the group ring. And so what Takaozawa proved in 2016 is he proved a new characterizational property T in terms of sums of squares, okay? Sums of Hermitian squares. So he showed that such a group has to have property T if and only if you have a positive constant and finally many elements in the group ring such that delta squared minus kappa delta is a sum of Hermitian squares of these elements in the group ring. Okay? So this thing here, being a sum of Hermitian squares, this is a notion of positivity inside the group ring. Okay? If I would complete my group ring, right? If I would have CG and I would complete it to a C-star algebra, my notion of positivity is just being A star A, right? I can always find the square root inside a C-star algebra. But here we're in the group ring in a completely algebraic setting, and this is the correct notion of positivity that we want to use, being a sum of squares. So slightly similar, but slightly more general. So it's slightly more flexible for this setting. Okay. Now the key thing here is that once you examine this condition, this is finite dimensional, right? So delta squared. So delta is supported on the Laplacian. The Laplacian is supported on the generators. Delta squared is supported on the generator square, obviously. And here I have just squares of finitely many elements, which also have finite support on the group. So this whole equation lives on a finite subset in my group, right? So this was actually quite surprising, a really stunning result, because it turns out what it tells you is that this very strong property T, is decided on a finite subset of a group, right? That's what it tells you. So this is pretty amazing. Okay, so Taka, when he wrote his paper, he suggested right away that maybe it's possible to use computers to help with finding new examples of property T. And that's the strategy that we were using. So how do you actually do this? Okay, so let's start with an element which I want to say is positive. So I have an element which is a sum of squares. Okay, and these psi i's are supported on a finite subset of G. So I can rewrite this whole equation in terms of matrices. Okay, so I can say that this is equivalent to the existence of a positive definite matrix, which is indexed by this support, and it has real values. Okay, and in the sense that eta is B, P, B transpose, where B is the vector consisting of the basis elements, so just the group elements from my set E. Okay, why is that the case? Because once I have a positive definite matrix, I can find the square root, and I can rewrite this in this form, and then the ith column of Q will give me precisely the coefficients of psi I. Okay, but so now my task is to find a positive definite matrix which satisfies some equation. Okay, so what I can do is I can actually use convex optimization over the column of positive definite matrices to try to find such a matrix. Okay, so I can try to find a matrix P which satisfies this equation and is positive semi-definite. Okay, so this convex optimization over positive definite matrices, this is called semi-definite programming, and there are specific solvers that essentially do this, right? So they are written with various purposes in mind. They are implemented in various programming languages like Python or Julia, and you can just use one off the shelf. So they have different properties, different convergence properties, and they use different methods. But you can just use one of these solvers. Okay, so assume now. Okay, so let's say we took this data and we plugged it into the solver, and let's assume that we have found a solution P. Okay, so now we know that eta. Our solver has determined that eta is the sum of squares of psi. Okay, the problem is there's a numerical error involved. Right? I mean, we made a numerical computation. This is not a precise solution. Right? So that's not good because in a way, I mean, it doesn't give us a proof. However, there's a little bit of magic happening. Okay, and because of the setup that we were working on, and it turns out that if the solution that we found was sufficiently good, we can actually deduce the existence of a true solution nearby. Okay, so this is done using this lemma here, which says, so this was proved by Taka and then improved by Netzer and Tom. So they did this quantitative version here. So what Taka showed is that the Laplacian is an order unit in the augmentation ideal. So the augmentation ideal inside the group ring is the set of those functions whose coefficients sum to 0. Okay, and if you have a self-adjoint element inside the grouping, that it turns out, inside this augmentation ideal, it turns out that you can add a sufficiently large multiple of the Laplacian, and the sum will be a sum of squares, okay, if you choose R to be sufficiently large. So this is a phenomenon that we know from linear algebra, okay? So if you have a matrix whose eigenvalues are real, you can add a sufficiently large multiple of the identity to it, and then the eigenvalues of the sum will be positive. Okay, so this is the same statement, but now it's happening inside the augmentation ideal, inside the group ring, and we're using the Laplacian as our order unit, and this is the notion of positivity that we have here. Okay, and then this quantitative version here says what is the smallest R that we need to take. Okay, so with this in mind, we can try to improve our search and try to show that something is strictly positive, and you can do this, right? So we correct our equation a little bit, and but here's where the magic happens. So now assume that we have found our solution. Okay, then I can write this solution in terms of. So if I forget the blue parts, then this and this cancels, right? So but I add these two guys artificially, and then this part is positive. This part lives by some argument inside the augmentation ideal, so I can add a sufficiently large multiple of the identity here, of the Laplacian here to make this positive, and then of course I have to add the same on this side, but here I have minus lambda times delta plus R times delta, and this just becomes lambda minus R times delta. Okay, so this is positive, this is positive. Now, the only question is, if lambda minus R is still positive, then I have property T. Okay? And, well, this R, from the lemma, this R depends on how good my solution is. Okay, so essentially, if my solution is sufficiently good, and that's measured in the size of its support and the L1 norm of the solution, of the numerical error, then I do get a proof of property T. So what is important is that this L1 norm on which the error depends is computed in interval arithmetic. So this gives a rigorous proof of positivity of this element. Okay. So another issue that we end up. So now we know that we can do something with this, and then we want to use this strategy in audit 5, And the issue that we run into is that the ball of radius 2 on which we're trying to find a solution is huge. Okay, it has 4,641 elements, which means that if I want to do convex optimization over matrices of this size, each of these matrices has almost 11 million entries. Okay, so this is too much for any of these solvers to handle. So the task that we needed to perform is to somehow reduce the number of variables. And what you can do is you can reduce the number of these variables by symmetrization. So there's some finite group that acts on the generators of the free group by inverting them and permuting. And it also then this action translates to plot of 5. It preserves the problem, and we can show that if there is a solution to our original problem, then there is also a solution which is invariant with respect to this action. Okay, so that's great, but this raises another problem. So you cannot really just take matrices that are invariant with respect to some group action that you made up and plug them into a solver, because these solvers are only be able to work with algebras of matrices, so the full algebras of matrices, not with some subset which is invariant under the action of some group. However, we can use a classical theorem here, so we can decompose these gamma invariant matrices using the Wedderburn decomposition. So we can show that so from the Wedderburn decomposition, you get that the C-star algebra generated by the permutation representation on this set splits into a direct sum of matrix algebras. Okay, so and out of this you get what happens is your problem splits, your large problem splits into a direct sum of many smaller problems. Okay, so here's a picture which should suggest this, and the reduction in the number of variables for audit 5 was drastic. So we went from almost 11 million variables to 13,232 variables by doing this symmetrization. So with this, we were able to actually plug this into a solver and put together a solution. Okay. All right. So this is the theorem that we proved in the technical statement, and then maybe I'll. I don't want to get into this, but because that's a little bit more involved. But to do the infinite case, because of course we can do this using a single computation for a single group. But then to do the case of the infinite family of groups, we needed to have a procedure that somehow would allow us to induce property T for all the indices above a certain point from a single computation. Okay, so this can be done by looking at the subgroups. So in ODFM, there's many copies of ODFN for n less or equal than m. And then what you can do is you can decompose the Laplacian into in ODFM into copies of the Laplacian in ODFN. Okay, and then. And then we can also, so there are some other elements that we can identify inside the group ring, which also have this decomposition, they satisfy this kind of decomposition scheme. And then it turns out that what one can do is one can simply compute or show positivity of a single element in the group ring, and suddenly you have property T for all groups above a certain index. Okay, so what time should I stop?
2 minutes.
2 minutes, okay. Okay, so maybe, so these are somewhat technical, but maybe what I'd like to mention are some applications of what we did. So one of the applications goes back to a question posted by Alex Lubotsky and Igor Pak. So there's an algorithm called the product replacement algorithm, and it's an algorithm that whenever you have a finite group, it can produce uniformly distributed random elements on the group. Okay, so it kind of allows you to just pick a random element with the expectation that it really will be random. Okay, so Lubotsky and Pak in 2001 showed that. So the algorithm actually was designed in the 90s, and it works surprisingly well in the sense that it is very fast, and it exceeded expectations in terms of how fast it was working. And in 2001, Lubotsky suggested a solution or an explanation why this is the case. So they showed that actually property T for odd Fn would explain this. And the reason is that this they noticed that the product replacement algorithm is implemented by a random walk via a quotient of odd Fn. So one of the applications of our theorem is that this explanation is indeed true. And perhaps I should stop here. Thank you.
Okay, thank you very much. So, are there any questions, comments? Yeah.
Perhaps it's a very naive or stupid question, but in the case of semi-simple groups, you mentioned that if they have rank greater or equal than 2, they automatically satisfy property T, right? So is there a simple idea of why SL2R or SL2C do not satisfy property T?
For SL2Z, so SL2Z has a free group on 2 generators as a finite index subgroup. Right, so if it's an index 12, you can point out 2 specific matrices, and so if it's a finite index subgroup, then property T would, it passes in both directions through finite index subgroups. So in particular for SL2C or R, you would get this through the lattice argument. So yeah.
Okay, thank you.
Further questions?
Working on this mapping class group now?
Well, so if you look on archive, there is a paper by Marek and David, and so they were working on extending this to the mapping class group. I think there's still so their paper is on Chevalier groups, and I think for mapping class groups it still doesn't work. So they are more complicated in some ways. And I know that within the community, the expectations are split whether they actually should have property T or not.
Anybody else? Okay, so before we thank the speaker again, let me say that if you want to hear more about Piotr's research, more recent research, you are welcome at 12:30 to another talk today by him at the Geometric and Combinatorial Group Theory section, so during the section time. And there is also an announcement from organizers, but first, thank Piotr again.
So we are starting our sessions, thematic sessions in, I think, 12 minutes in the building of mathematics. There is still a chance to choose an excursion. If you wish, you have to write your name on this whiteboard near the reception. And